So, let's get started with today's class. Before we start today, let's do a very quick recap of everything we've seen so far. Okay. So, we started by looking at basics of quantum information. Like we're really studying computer science in this, well, in this course, in this department. And quantum computing is a fundamentally new way of doing computing, one that nature supports. So, we started by looking at what is a mathematical model that captures this quantum computation. Then we progressed on to quantum algorithms. We saw some quantum algorithms that make use of these some extra powers to speed up things that classical computers do, right. Then we switched our focus to cryptography. So, we tried to look at how to build some cryptography. We looked at some of the standard crypto systems that are out there, RSA, El-Gamal and so on, right. So, we in particular we saw encryption schemes from these assumptions, and then we went back and saw how to break these assumptions using a quantum computer, right. So, this brings us after that, even after that, what we did was we saw how to protect against quantum attacks, right. So, we talked about a few post quantum assumptions. We did not get much time to go into it in very much detail, but we looked at lattice based assumptions. We talked about what are the hard problems, why we believe they are quantum hard, right, and we saw how to build a little bit of crypto even from that. So, now we've come to kind of the last main topic of the course. It is also about time, given that the course is almost coming to an end. So, as I promised right from the beginning, what we will do now is look at some quantum cryptography. So far we have really focused on quantum computers breaking cryptography. But of course, if you have quantum computers, then you can also use it to do useful things like making building cryptography. And the next few lectures that we have, we will look at some of the some interesting cryptography using quantum computers. Okay, so in particular, just a high level road ahead. Okay, so we'll look at QKD, quantum key distribution. So, remember we looked at key distribution using classical assumptions. We looked at Diffie-Hellman key exchange, right. We'll talk about quantum key distribution. This is one of the most famous results in quantum cryptography. Many of you may have seen it before, at least in some form, right. The point of quantum key distribution is that it's much more powerful than classical. It gives you information theoretically secure keys. So, this means that the attacker is not considered to be limited by computational power. Like when we saw Diffie-Hellman key exchange, the attacker, if she has unbounded time, if she has exponential time, she can figure out the key. How? Just by solving the discrete log problem, right. So, with quantum key distribution, you will get information theoretic security. So, this is one of the sort of big things about quantum, and this is an old protocol. I mean, the first protocol is an old protocol. Since then, of course, there has been a lot of work, but anyway, we will see a little bit of this. Then what we will see is quantum one-time paths, right. So, again in the classical setting, we have seen how to use one-time paths for privacy of messages, and then we will see quantum secret key encryption and quantum public key encryption. Okay, so, this is a minimum thing that we will do, and if time permits, we will try to see at least one more advanced application like quantum FHE or quantum money. So, in my previous my plan for the course, I was hoping to show you both of these. I do not think we have very much time left, but we have seen classical FHE. So, if time permits, at least one lecture I would like to do at least some of the main ideas of quantum FHE. So, here all of this is like when we talk of encrypting a quantum state, right? That is when it goes into the realm of quantum cryptography. So, this is not a question of doing classical encryption which is secure against a quantum adversary. It is about a quantum computer performing encryption, right, and you would like the encryption to be of a quantum state, not of a bit or a classical string or something. Okay, so this is where we are headed. So, let us get right to it. So, before we delve into any of these applications, we need to first generalize the notion of a state. Okay, so today we will talk about mixed states. And a mixed state is a very nice generalization of a pure state. So, a pure state we have written it, you know, as a linear combination of basis vectors, you know, satisfying some algebraic constraints. Now, it turns out that these pure states are not sufficient to capture everything that occurs in nature. For example, you know, processes in nature are random, like they are noisy, for example. So, you could have a situation where you know, you get state 0 with probability half and state 1 with probability half. Like, you know, think of information theory and, you know, channels. You are sending something over a channel and, you know, it can get flipped, right. So, then the receiver can get one state with some probability and another state with some other probability, things like that. So, our first task is to characterize these states. We will go into it a little bit because these will be very useful. These will be very useful in developing cryptography later. Okay, so let me define a mixed state. So, first let us say that we have some sort of noisy device and it outputs, you know, psi 1 with probability p1, okay, psi 2 with probability p2 and psi n with probability pn. Okay. So, how do we capture or represent such a state? Well, I mean, one immediate way in which we can do it is we can represent simply by this tuple, right. So, I mean, you could certainly write it like that. This is, I mean, this is almost like a brute force type of representation, right. You are just listing it out that, okay, this state with this probability. Now, there is a more compact and you know, useful way of representing this. This is using a certain matrix which we will later study as the density matrix. So, let me first just define this matrix. Okay, so let us say that we measure the above device in basis V1 up to Vd. Okay, so now what is the probability that you know, Vi is observed? Any guesses? So, in the case of a pure state, basically one of the Pi's is 1, isn't it? I mean, there are the other probabilities are all 0, that is a pure state. Now, we are trying to figure out the probability of measuring, like getting a certain output when we measure a mixed state in a given basis. So, what do you think this this looks like? In the case of a pure state, what does it look like? Like if I just have psi I and I want to compute the probability of getting Vi, what does the probability look like? Inner product? Good. So, the inner product of Vi and psi, you know, mod squared. Good. So, now let us generalize this. What is a very natural way to generalize this to this mixed state that we are looking at? Exactly. So, you simply sum over all the states weighted by the probabilities, right. So, that is correct. So, what we will do is we will say we will define this probability as summation over j p j, okay, V I psi j the whole squared, okay. So, it is a very natural generalization. And now this in turn can be written as summation over j p j, right. I am just expanding this out. So, I am just rewriting this. Oh sorry, there is no square right now, V I. Good. Does everyone agree with this? So, this is just simple linear algebra, right. So, this is our probability, and I'm going to refer to this matrix as some row, some matrix row. Later we will see that this is called a density matrix corresponding to this mixed state, okay, and yeah, we will see some properties about it. But right now I just want us to observe that the probability of getting a certain state is that state, right, times this matrix, right, times ket of that state. So, the bra of the state times the matrix times the ket of the state, okay. So, this is our probability. A nice thing that you should observe here is that this matrix is completely it's completely determined by the pi psi I, right. So, it's purely a function of the state, right. So, it is unique in that sense. Okay. So, now let's just use this to write down a definition. So, the mixed state pi psi I is represented by this matrix, okay, and this matrix embodies everything that that you need about the mixed state, okay. So, it suffices to just focus our attention on this matrix, and as we will see, it can happen that couple like that multiple mixed states end up having the same matrix, that can happen, in which case in fact those states are not distinguishable to an observer. So, even though the matrix is losing maybe some information, we will see some examples of that. It turns out that it suffices to just focus on this matrix because this is what can be observed, okay, good. So, let us very quickly see a simple example of this, what I just said, okay. So, if I have S1 which is 0 with probability 1 and 1 with probability 0, okay, then what is the row? This is just 0 0. Sorry, I keep swapping the rows and columns, okay. So, this is just 1 0 0 0, okay. This is just a very simple example. And now if I have another one, right, which is minus 0 with probability 1 and 1 with probability 0, then the rho is minus 0 minus 0, which is the same matrix. So, this is a very simple example. I mean, in fact, these are pure states, right. So, I mean all the weight is on one state. Okay, maybe for the sake of avoiding triviality, let us just look at one which is actually a mixed state. So, let us say that S3 is 0 with probability half and it is 1 with probability half. Okay, then its rho is going to be half 0 0 plus half 1 1, okay, and this is going to end up being half 0 0 half. Any questions? So, it is a very natural generalization, yeah. Okay. Now, one thing that we also need to specify is how do these mixed states evolve, right. So, we defined the mixed state and we talked about how to generalize measurement. By the way, I just want to remark that we are looking at measurement in a fairly specialized way. In the theory, there are more general ways of performing measurements, which for our purposes are not really required. So, we are not getting into that, but I just wanted to remark that. So, we looked at some simple generalization of measurement which suffices for us. And another thing that we need to look at, as I just said, is how do these states evolve. So, in the pure state case we were applying unitaries, right, to get other states. So, for mixed states as well we should figure out what happens if we want to apply a unitary, right. So, how do states evolve? So, again you will see it is very natural. So, suppose I have a mixed state S1 which is Pi psi I, and this goes through a unitary U. Okay. So, now this transforms to some S2 which is Pi U psi I, right. I would like you to tell me how does the matrix corresponding to S2, how does it look in relation to the S1 matrix. So, let me just give you some notation. So, let rho S1 be, as the name suggests, the matrix corresponding to S1. Okay, let me say SB. Okay, so B in 1 2. Okay, so rho S1 and rho S2 are the matrices. I want you to tell me how to represent rho S2 in terms of rho S1. Can you quickly compute and tell me? Yes, I do not know, that was a very quick, you have seen this before? Very good. So, that is exactly right. So, it will just be U rho S1 U dagger. It is indeed very natural. Okay. So, everybody can check this offline then. Yeah. So, it is very intuitive.